In this video we shall overview index types. Let's start with a quick reminder. So, an index is a specific kind of physical access path to improve the speed of access to data that is physically stored somewhere. And like in real life, index is a kind of a map for a human that helps us finding objects of interest quickly and easy. Before we begin, we have to emphasize a disclaimer here that this is just a short, brief, quick overview. Under the hood, there is a lot of mathematics, algorithms and a lot of other stuff, and it really may take years to comprehend. So this is just a short overview. And the idea is to make you interested in those mathematics, algorithms, and find out those ideas yourself. Here is a quick overview. Indexes may be organized by fields count, records uniqueness, records order, storage, density, hierarchy, correlation with query. You see, there are a lot of indexes. Indexes may also be organized by basic structure, like this, or by specific functions, like these. And we shall overview all those and these types in details right now. By fields count, indexes may be either simple or composite, compound. With simple index, you may see that this index contains information about one field only, but with composite index, it contains information about several fields inside. And there may be another implementation. With nested trees, we have a tree and subtrees within those nodes of the basic tree. It only depends on physical implementation and on what your DBMS either supports or no. By record uniqueness, indexes may be either unique or non-unique. With unique index, that index does not allow duplications of indexed data. So, such indexes are usually put on unique fields. Non-unique indexes allow duplication of some records, some data in indexed fields. So that's the main difference. No duplications here, but some duplications may be with non-unique indexes. By records order, indexes may be primary, clustered and non-clustered. Those will be in a couple of seconds. Primary index is unique index, so no duplications here, and in such index the index order is the same as data order. In clustered index, the index order is the same as data order, but clustered index usually allows duplications of data. Speaking generally, clustered index may be or not be primary, and vice versa, primary index may be or not be clustered. In such case, in some DBMSs, the index engine will add some specific values to make those records unique. But once again, it depends on the implementation and on the capabilities of your DBMS. The main difference between clustered and non-clustered index is that with clustered index, the index order is the same as data order, and in non-clustered index, the index order is maybe like this, and you may see that this is not the same as data order here. So the correspondence or no correspondence of index records and data records is the only difference between those indexes. And we shall emphasize that any table may have only one clustered index, maybe 0, but no more than 1. And each table may have as much non-clustered indexes as you wish. By storage, there are a lot of combinations. Maybe single partition index and single table partition, maybe partitioned index and partitioned table. You may put such table partitions on different HDDs or SSDs or any other physical storage. And there may be such variations as partitioned index and non-partitioned table, or non-partitioned index and partitioned table, and so on and so on and so on. It all depends on the implementations and DBMS capabilities. By density, there may be sparse and dense indexes. With sparse indexes, we index only some range of data. So you see, this record and this record are not indexed. So that's sparse index. With dense index, we also index each and every record in a physical table. So that's the only difference. And the most common case for sparse indexes is the situation when we index not only a range but a set of similar records. With dense indexes, we always index each and every record. Why do we need sparse indexes? Because they are usually smaller and easier to update. But nowadays, most DBMSs always use dense indexes only because of course, they are larger, they are harder to update, but they increase the search speed much better than sparse indexes do. By hierarchy, there may be one-leveled and multi-leveled indexes. One-leveled indexes include primary, hash table-based indexes, clustered, bit mask-based indexes, and so on. So you see one level here only. With multi-leveled indexes, such as B-tree-based, R-tree-based, T-tree-based, XML indexes, we have several levels here. So this is level 1, this is level 2, this is level 3, and there may be a lot of more levels. It also depends on the implementation and on DBMS capabilities. By correlation with query, the same index may be either covering or non-covering depending on the situation. Let's compare two situations. The first is covering index. Here we have a table with data, here we have some one index and some two index. And let's review such query, the query A. We wanna know how many users are there, how many IDs, in the range between 2 and 10. How can DBMS execute this query? The DBMS may use this clustered index and count those IDs. The DBMS does not need any other information. It may use index only, so this index is covering for this particular query. The next example. We want to know the status of user with such an email. We have compound index here, so DBMS may find that email, here it is, and take the status right from the index. It doesn't need any other data stored in the table. So this index is covering for this query. But here is no covering example. We want to know the login of a user with such an email and such a status. Of course, using this index, the DBMS will quickly find that user, here it is, but his login is not stored in the index. So the DBMS should open table file, search for this record and read this data to execute that query. So this index are non-covering for this query. By basic structure, there may be the following index types. Let's start with balanced tree. How a balanced tree looks like and why is it balanced? So let us schematically draw a balanced tree. And why is it balanced? Because if we put a string here, for instance, or we cut out this and put a string here, for instance, you may see that there is balance. There is no such situation when, for instance, we have a few of branches here and a lot of branches here. That's not balanced tree. This is. So, balanced tree may be the following types with equal nodes. As you can see here, each node contains the byte offset of a physical record. Each and every node on each and every level. So these are equal nodes. But in this case, nodes are non-equal, because on the first and the second levels, there are no byte offsets here. So these levels are used for search purposes only, and only on the third level we have really byte offsets, so those nodes are non-equal. T-tree indexes are the most modern version of B-tree indexes, because B-tree indexes were developed a long time ago, and the idea behind B-tree indexes that each such block, a small or a huge one, may be stored separately on HDD and may be read into random access memory separately. With T-tree, we suppose that the whole tree is stored in RAM, not by blocks, but the whole. So the inner structure is somehow different, but the main idea is the same. We have some multi-level index with some bytes offsets, and we can use that index to find the data quickly. R-tree index is usually either B or T-tree based, but the idea is to have some space and some objects in that space. Then the space is divided into some regions, and so on, and information about those objects and regions is stored inside the index. So one can easily find the nearest objects or where is that object stored, and so on and so on and so on. And in the real life, for instance, maybe you've got such a situation when you open your mobile phone, any application, and you wanna know if there is some gas station near you or some shop or something like that. So that's the real space, that may be a gas station or some cafe or something like that. And R-tree indexes in your mobile application are usually help to find this information quickly. Hash table indexes are based on some hash function. So indexed value is coming into that hash function, then a hash comes out, and the hash values are used to create the whole index. We may compare hash table based indexes with balanced tree indexes. As long as balanced tree is a tree, indeed, balanced tree indexes are good for such operations as less or more, because when we go left, it's less, when we go right, it's more. So B-tree indexes are good for such operations. Hash table indexes are bad for such operations, but they are good for equals operations. So it depends on if you have more equals operations, you may be going to use hash table index. If you have more less or more operations, then maybe you should use B-tree based indexes. Bitmask indexes are good for the situation when we have a lot of data, but with few of varieties. Imagine that we have several billions of records for day of weeks, like Sunday, Monday, and so on. 7 maximum. There are no more days of weeks. So bitmap indexes are good for such situation, when we have small varieties, but a lot of data. Column store indexes are easy to understand in comparison with balanced tree indexes. Balanced tree indexes usually have information about several fields of a record, but there may be situation when we do not want to use several fields. We want to use one field only, one field only. So column store index stores in compressed form information about each separate column. And here is the example. For instance, we have some payments and we want to know something about money only. The minimum, the maximum, the average value, and so on. So using column store index will help us in this situation perfectly. To understand indexes with included columns, you should remember information from a couple of minutes ago about covering and non-covering indexes. If we want some index to become covering for a set of queries, we may want to add some additional data into that index. In order for DBMS to use the index only without real information from that hard drive, the information from that table, to execute our query. Not a lot of DBMSs support such indexes, but if your DBMS does, that's maybe good in some situations. In some cases, we want to index something that does not exist in a table yet, maybe a result of some function calculation or some computed column calculation. So imagine we have a list of people and we have some information from their name and middle name to form the initials, but we do not store initials in that table. It's a computed column. Nevertheless, if we want to search some people quickly by their initials, we may use an index on computed columns, or maybe an index on a function value. The idea is the same. So we may index something that's not really exist in the table. Filtered indexes allow us to have a lot of data, but store information about only several records matching some criteria. Imagine these people are people of interest for us. Maybe they are somehow extremely good or extremely bad, it doesn't matter. We want to know something about only Petrovs and Sidorovs here. But we do not want to know anything about a lot of people, millions or even billions and so on. So we may create such a small filtered index. It's really small, it fits into the RAM perfectly, it's easy to update, it's easy to create, but it will help us find only this person and no other person from this table. The idea of spatial indexes is the same as of R3-based indexes. We have some space, we have some real objects in that space, then we divide that space into some polygons and store the information that will help us to find some object, to find out if one object includes another, and so on and so on and so on. And all this we may achieve with spatial indexes. Full text indexes help us to search through text. Imagine we have a lot of messages from some messenger here. We shall first eliminate stop words, because those stop words may be in each and every message, for instance, but other words are indexed. And if we want to know, are there any messages containing clarifying word? Okay, here it is, and we may see that here it is. So we can search through text quick with full text indexes. Domain indexes supported by a few DBMSs nowadays are usually just an index, any index, with a specific API for some algorithms to add to perform such tasks as maybe full text search with word form consideration, or time intervals analyzing and processing, or serialized data indexing, or some binary documents analyzing and indexing, and so on and so on and so on. So you have an index, you have an API, you add some algorithm, and you get a domain index. XML, or in some cases JSON indexes, are tricky ones. Someone may even say that neither XML nor JSON are relational database compatible things. But nevertheless, because such formats are extremely popular nowadays, such indexes exist. As you can see, they are rather complex indexes, and they are usually multi-level indexes, usually with 2 or maybe 3 levels. On the first level, some records are indexed, and on other levels, the contents of XML or JSON file is indexed. And please remember that new index types appear almost every month or even day. So you may find some other indexes that are not in this video because they appeared after the video recording or they were omitted for several reasons. Nevertheless, please always carefully read through documentation about your DBMS, about index types your DBMS supports, and use those indexes to increase the speed, the performance of your database.